Imagine a class of students. They will have different personalities and attitudes. Some will participate and cooperate with the teacher. Some will be less interested in what the teacher says and does. The teacher will try to involve them, for example, by explicitly addressing them by their name. Or suppose two families at a museum. People will have the tendency to interact with other people in their family. The robot might try to make them interact with each other. Welcome to my presentation about controlling the conversation dynamics. I'm Antonio Sgorbissa from the University of Genova. Multi-party conversation is receiving increasing attention in social robotics, with researchers focusing on how to track and recognize participants, how to engage them, how to manage conversation turns, how to recognize the dominant role of participants, and finally, how to control the conversation dynamics. To this end, we propose an approach that relies solely on speech analysis. The architecture is based on a client, the robot, and a cloud server. The client starts recording audio from people and it sends it to the services for speech-to-text translation and speaker recognition. A text sentence tagged with the corresponding speaker is returned, which is then sent to the server. The sentence is sent to the dialogue manager that will produce a verbal reply, and it's also sent to a planner that will produce a plan. Finally, the verbal reply and the plan are returned to the robot client, which can use them for interaction with people. Note the role of the dialog state in this process, which is exchanged between the client and server to ensure that no information is stored on the server. Let's see the role of the dialog manager in controlling the conversation dynamics. The key element is the dialog state. The dialog state contains information about each speaker who spoke with the robot, their speaking time and number of words spoken. Remember, we can have multiple speakers. This information is stored for a moving window. The system knows who spoke in each turn, which can be used to compute F and W, the speaking time and number of spoken words within the moving window. And finally, the dominance D of each speaker, a weighted sum of F and W. Let's go back to the dialog state. It includes a matrix that tells us how frequently a speaker speaks after another speaker. Thanks to the Louvain algorithm, we can use this information to partition the set of all speakers into communities, that is, clusters of speakers that tend to speak in subsequent turns. The balancing policy considers the dominance and it selects the speaker whose dominance is lower, meaning the one who has spoken less. The robot will address this speaker to balance participation. The community policy considers the set of communities that have been detected. It picks one community and a speaker belonging to this community, with the constraint that the speaker addressed in the previous turn should not belong to the selected community. This ensures that, in subsequent turns, the robot will address speakers belonging to different communities. Both the balancing and the community policies come in two versions. The so-called soft version states that when the robot addresses a person and the wrong person replies, the robot is happy to talk with this person. The hard version states that when the robot addresses a person and the wrong person replies, the robot will tell this person it's not their turn and address the original person again. Experiments were performed with 300 students divided into 75 groups of 4 students. We divided the groups into 5 arms: a neutral arm with no balancing or community policy applied, 2 arms with the robot applying the balancing policy, both in hard and soft versions, 2 arms with the robot applying the community policy. A fixed approval was obtained for the experiments. We measured the dominance error between the most active and the least active speakers, which is 0 when all speakers are equally active, and the number of communities error, which is 0 when all speakers are considered to be part of the same community.
Ho capito, Kevin. Vorrei sapere il nome del posto in cui vivi. E l'Italia?
Sì, è in Italia. A Genova.
Scusa Isaac, ma la mia domanda era per Kevin. Vorrei sapere il nome del posto in cui vivi. E l'Italia?
Sì, è in Italia, vivo a Genova.
We plot the dominance of each speaker, which shows that, with a neutral policy, the dominance error is never 0 because it depends on the attitude of each speaker. However, when the balancing policy is active, the situation changes. And this is true for both the hard and the soft versions. Similarly, when no community policy is used, the community error is higher. Speakers are detected as belonging to different communities. The situation changes when the community policy is applied, both the hard and the soft versions. In conclusion, a cloud system for multi-party interaction with people has been presented. The cloud architecture has been described by outlining key ideas, including 2 policies for controlling the dynamics of the conversation. The whole system was tested with 300 middle school students, which confirmed the feasibility of the approach.